I'm sorry, you were saying?
Ray tracing.
I don't think so. Ray tracing is very complicated for multiple lenses. I'd like to avoid that.
The lens mirror equation then?
We might do that, but all he's asking here is for a qualitative answer. He just asks, would you have changed the size? So let's see if we can just answer this qualitatively. Sleep, science. What type of image is this going to be from the object one, real or virtual?
Real.
Now this is image one and object two. You see why I call it that? It's the image from lens one, and it will be the object for lens two. Okay, so this is the image from this lens. So let's think through that carefully. Is that a real image or a virtual image? How can we tell?
So the light's going through that area, so it would be a virtual image.
Because a virtual image is on the opposite side of the outgoing light. Well, the light is outgoing here on the right, but we need to put the image over here. Also, I think actually I guess I'm getting different students confused, but with some student I discussed corrective lenses always make virtual images. Corrective lenses always make virtual images because the light always goes, say, to the right-hand side of the corrective lens, but you're trying to put an image at the near or the far point, and the near or the far point is out here. Since the near or the far point is always on this side of the corrective lens, and the outgoing lens on the other side, corrective lenses always make, I don't remember if us two talked about that, but a corrective lens always makes a virtual image. While we're at it, the lens of the camera always makes, or the lens of the eye always makes a real image, because the image here is supposed to be on the film or the retina, and that's on the same side as the outgoing light. So those are some important ideas. The eye lens or the camera lens is always making a real image, because it has to be on the camera or the film, but a corrective lens has to make a virtual image, because that's where the near point is, or the far point, out here. So let's take out our chart and ask what type of image is this going to be. We're getting a virtual image from a converging lens. What else do we know about virtual images from converging lenses?
They're upright and magnified.
Yeah. There's only one situation when you can get a virtual image from a converging lens. That's when you're inside the focal point. So that also tells us that the focal point for this corrective lens has to be way out here. The focal point for that corrective lens must be out here, further than 60. Otherwise, it wouldn't give us a virtual image, which is what we need. Okay, so if I was going to draw a picture of it, it's upright, so it's pointing in the same direction as the original object, and it's magnified, so it's bigger than the original object. All right, now I think we should be able to answer the question. Sounds good. So they're asking us to compare how big is the image with this combination of the corrective lenses compared to if there's no corrective lens and we just put the flower over here. Well, I think it's pretty clear. If we just put the flower here, it would only be this big. If we just put the flower here, it would only be this big. Now the camera lens is seeing a bigger object. So it makes sense that since the camera is seeing a bigger object than the flower, you'll get a bigger image than the flower.
So we figured out that it was bigger because we knew that it was a virtual image and then
for a converging lens. Yeah.
Upright magnified.
Right.
Is there another way to explain that it's upright and magnified? Like
well,
I mean, then
we know that we are converging. So
Right.
this is positive, and we know we're making a virtual image, so this term must be negative. We know this term is positive because it's the object distance. Okay, so we're putting a positive term and a negative term together to get a positive. So which of these two fractions is bigger? Which of the two fractions is bigger, 1 over s or 1 over s prime?
1 over s.
This must be the bigger fraction. 1 over s is bigger than 1 over s prime in magnitude. Now I'll put in the dots for magnitudes. So who's bigger, s or s prime?
X. No. S prime.
Why is that?
Because the inverse of it is smaller.
Yeah, so if a fraction is bigger, that's because it has a smaller denominator. If a fraction is bigger, that's because it has a smaller denominator. And again, now I'm putting in the dots because I'm just focusing on the magnitudes. The signs would just make this even more confusing. But we can just compare the magnitudes. This fraction must be bigger in magnitude than this one, which means it must have a smaller denominator in magnitude. So how does this help us to prove that the image is bigger than the object?
Because if you use the magnification equation, then that will give you a positive answer.
Not quite, because the positive or negative for magnification would be whether it's upright or inverted. What do we care about? We care about the magnitude of the magnification. What's the formula for the magnitude of the magnification?
Negative s prime over s.
Now actually,
Oh.
since we're just focusing on magnitudes, we would leave out the negative sign. The negative sign is just very confusing. It's certainly confusing to me, so I'm just going to focus on magnitudes. Why don't I care about the negative? Because that just tells us whether it's upright or inverted. When you want to see whether something's magnified or shrunk, you can leave out the negative sign and just focus on the magnitudes. Well, now we can clearly see that the numerator here is going to be bigger than the denominator. So we're going to get, so that's another thing to review once more in your notes. Magnification doesn't mean a positive magnification. It means, so enlargement doesn't mean a positive magnification. It means the magnitude of the magnification is bigger than 1. And shrinking means the magnitude of the magnification is smaller than 1. So there's the proof right there. That's how that part of the chart got proved in the first place. So these are difficult, but now we've seen a couple of examples of how to do that.